Okay, the pendulum. Got that? Yeah. You all know this word pendulum? Yeah. Where do you see it in the home? Yeah, in the clock maybe. Yeah. Anywhere else you might see it nowadays? Apart from a clock? No, can't think of anything. Hypnotist, you're getting sleepy. Yeah, maybe, something like this. Huh? No, metronome would kind of like be a pendulum. I wonder would it have the same... Maybe, yeah. I never really thought about how a metronome works. You adjust the weight on it. So, yes, actually it might be like a pendulum, just upside down. Okay, so these are the key words here for the pendulum. What do we need to have? So, in the pendulum, we usually consider the rod to have no mass, and then the bob at the end has all the mass. This is the equilibrium position. The amplitude, how far out you pull it. There's no friction. Everything's smooth. Now, of course, in real life, that's not true. What do we call the process of it slowing down? Damping. Yeah, caused by friction. Yeah. Okay, well, we'll start by just drawing this in your notebook, please. What will I dress up as on Friday? I want to do something outrageous like Sir Isaac Newton, but I think that costume would be too expensive. You know, like the wig and the coat and everything. Huh? Yeah.
Hawkins.
I did Hawkins one year. I printed out a Hawkins mask, and I got one of the chairs from the office, and I got the voice program on my tablet, and stuck that on the arm of the chair. So I could be the ghost of Stephen Hawkins. Yeah, sorry, it's not clear, but it's the length that's pulled out. So you can think about it as either the maximum angle or the maximum distance out here. Depends on the context. Okay, what I'm going to do next is a proof. This proof is quite important because you'll need this proof in one of your lab reports, you know, when you do your experiments next semester. So one of the experiments is involving the pendulum, so you need this proof. So you want to write this proof down carefully so you can type it up later, okay? So let's start with our pendulum, and we'll say it has a length L here, and we'll call this angle here theta. And this distance here is L sine theta. And this distance here is L cos theta. This pendulum has a weight, which is mg, and it has a tension here, which is T. And I can resolve this here and here. So this direction, if that's theta, then this angle here is theta. So this, that's actually, if the T is there, then this is T cos theta, and this is T sine theta. Okay. Now, what I'll do is I'll call, okay, so first thing is T cos theta will equal mg. Now, technically, that's not really true. It's really more like T cos theta is roughly equal to mg. Why am I saying that? Why am I saying that it's technically not equal? Is the bob moving up and down?
No.
Well, it is. Kind of, a little bit. As this swings down, the bob loses height. So the mg will be bigger than the t cos. And then on the way back up, what's happening? Yeah, the t cos will be bigger. But roughly speaking, they're about the same. Roughly. Okay? What is the T sine theta doing? That is a force making it move to the left, isn't it? Isn't it? Yeah. So, what you can say is the force is equal to minus T sine theta. Now, I'm going to draw this triangle again here. What I'm going to do is I'm just going to call this distance here x, and this distance here L, and this here is sine theta. Yeah? Okay. So, next part, let me think. Yes, next part. Okay, so now this part is a little bit tricky, but I'll just zoom out. So if you look at this triangle, what does sine theta equal? What's sine theta here? X over L. And what does cos theta equal? It will be this length over L. Okay? We don't know what this length is. Right? We could work it out using Pythagoras if we like. So usually we say that cos theta is roughly L over L. We roughly say that this is L. Now the reason we're saying this is again because we're not imagining this moving up and down, even though we know it moves up and down. But it's not really L. The only time that this will be L exactly is when the pendulum is down here. Yeah? But we've just said that we're not considering the up-down motion. We know it moves up and down, but we're imagining it doesn't. It's just going like this. Yeah. So we say that the cos theta is roughly equal to 1. Okay. So that means that T is roughly equal to mg by using this formula. So we get F equals minus mg, and sine theta we said is x over L. Now what did Newton say F is equal to? ma. So I can cancel here the m's. So this is the getting towards the end now. A is equal to minus g over Lx. Now what you can do is you can let omega represent root G over L. So then what does this become? A equals, what's that?
Omega squared.
Minus omega squared x. Now, have you seen that formula before, haven't you? What lesson did this come from? Simple harmonic motion. So what we've done is we've proved that the pendulum is moving in this simple harmonic motion because we arrived at this formula. But what's useful is we know what the omega is. It's root G over L. So using the formula for T, what would T equal? What's the formula for T? 2 pi over omega. So for this question, what would be the T? 2 pi over omega, so that's 2 pi root L, yeah, because it's over L over G. So we've just proven this formula for the pendulum. This formula gives us the periodic time as long as we know the length of the pendulum. You might have even seen this formula before.
But that disregards in the vertical movement.
Yeah, so it's only an approximation. So it's important that the pendulum appears to be moving only horizontally. So if you take your pendulum, oh here we go. If you take your pendulum and move it just a little angle, okay, it looks like it's moving horizontally. So you can use this approximation. However, if you do this, can we ignore the height now? No. No. But as long as it's a small angle, where it appears just to be moving horizontally, my approximations with the cos theta is reasonable. It's reasonable. So what's a typical small angle? You don't really want to be going past 15 degrees. You know, you want to keep the angle kind of small like this. Has anybody seen this formula before? No, really. This is a new formula. Really? Interesting. I thought this was a world famous formula in physics. You would have all done it. So you see why it's useful. If you just know the length of the pendulum, then you can know its periodic time. It was Galileo, I think, who discovered this first. I think. Was Galileo the one that was kicked out of the church?
Yeah.
Oh, yeah.
Yeah, it was him. Because
He said the Earth rotates.
that's it, yes. He discovered this formula. What he used to do when he was in church, because he was quite bored, is when the priests were swinging the incense, you know, the little chamber at the end of the string, he would time how long it would take. And he would guess the length of the, and he'd figure out, after a while he saw this relationship. So I just think that's funny. So he was the first one to discover this formula, but he didn't prove it the way we proved it. He just figured the formula out by looking at many examples of pendulums and realized, oh, it seems to be a relationship between the time and the length, you know. So because Galileo was obviously before Newton, so he didn't have formulas like simple harmonic motion and F equals ma. He only figured this formula out from the data, from observation. Okay, can we scroll down? Do you have that proof now? That proof's important. You have to type it up nice and neatly in your lab report. What do you think will be useful about this formula? Like what might you use it to calculate for an experiment? Mm-hmm. So the reason we use this formula is to calculate the G. Okay, let me explain with an experiment now. So what you do, your experiment, I'll just roughly draw it out here. You have a pendulum, and it has a length, and then it has a time. Okay. So what you do is like, firstly you would set L equal to say something like 1 meter. Then what you would do is you would swing it back and forth 10 times, and this gives you T10. And then what you do is you get t by just taking t10 and dividing by 10. Any ideas why we might swing it 10 times and divide by 10? Rather than just go 1 and time it. Yeah?
To prevent like error.
The error and the stop and the start. Yeah. Yeah. Then, after you do that, you then reduce the L, like say 0.9 meters. You know, you repeat, basically. So then at the end of it, what you have would be values of t squared, yes, you square the t, and L's. And the reason for that is in the formula t equals 2 pi root L over g, you can change that into t squared equals 4 pi squared over g L. If you plot this, where you put L on the x and t squared on the y, then can you see how this guy is a little bit like y equals mx? Because the t squared you're putting on the y-axis, the L you're putting on the x-axis. So what does this represent? The gradient, yeah. So what you do in the experiment is you plot these points and you find m. And then your m that you know will equal 4 pi squared, which you know, over g. So therefore you can estimate g. The value of g will be 4 pi over your gradient. Sorry, 4 pi squared over your gradient. So this is a simple experiment that can calculate the g for us. So you take your pendulum, you measure the time, you measure the length, and you plot time squared against length, and you'll find that you'll get a straight line graph. The gradient of this can give us the g. Has nobody seen this experiment before?
But not like this.
Then like what?
We did this experiment, but I didn't remember what we were finding.
But you just remember doing something with pendulum.
T-squared, because they didn't explain to us what it means.
Maybe you were just doing an experiment to plot t squared against L and to show that it's a linear proportional relationship if possible. So I think it's necessary that you make some notes, because what will happen in semester 2 is you're to do this experiment by yourself. In fact, you have to do 5 experiments. 2 of the experiments are together in one experiment, so to speak. So you'll do 3 experiments and then 2 experiments to measure G. And you'll write a lab report on the 2 experiments together measuring G in like one lab report. So you have to compare the 2 methods and, you know, which was more accurate and all this stuff, yeah. So the other way to measure G, of course, is just by dropping a ball and timing how long it takes to hit the ground. You'll see which one is more accurate. Now, I think the dropping of the ball one is not too bad, as long as the ball is dropped from a high enough height, not much friction, and you can time it well. The ball I have is a special one where the timer is on the ball. So you press a button on the ball and release, and when it hits the ground, the timer stops. It's on a display on the baseball. So it means you can get pretty decent times. Do you all have your laptops?
Yes.
Okay. Later today we have assessment support. On your timetable? Mm.
Placement.
Before that?
I can't disclose.
Huh? You know about this, don't you? What do you mean no?
So it's academic skills.
Oh, whatever the heck it's called. Sorry, Zach, These names are just made up. They don't have a particular meaning. That class, academic skills, I'll be taking you for it because we're going to get started on writing our physics essay. Now, I told Colin I don't really need the full 2 hours. So what I was thinking, I thought I'd check it with you, is, what time is that? 2 o'clock? So I was thinking we could do 2:15 to 3:45, 90 minutes. Because what will happen is we'll get started on the essay. I'll tell you what you need to write about. For the first lesson, really a lot of your time will be spent getting sources, research, getting maybe web pages, even videos, articles, just getting a rough idea of what you're going to write. Okay, but we'll talk through it later today. So I was thinking we'll do 2:15 to 3:45. Okay. I thought it said it was B401. What's it say in your timetable?
That's placement.
It's B401.
I thought it was,
Wait, what?
I thought it was B401 too.
Mine wasn't updated.
Ah, there you
I
go.
took it this Sunday.
Ah, that's old.
Really?
That's old.
Okay. How could I survive 3 days with this?
It's only the change for today, I think.
Yeah.
Okay, did you write that experiment down? Yeah. Now, here is a very simple question. We've already done the experiment. How long would it take a 1 meter pendulum to swing 10 times? So using the new formula, give me the answer here. 1 meter pendulum, swing 10 times. So you could get the time and then multiply it by 10. So just to be super clear in case you're confused, this formula, T equals 2 pi root L over G, that's the time to swing once. Okay? And I have a 1 meter pendulum and I want to know the time to swing 10 times. Okay? See what you can get.
What you said?
20 seconds sounds about right, yeah?
20.1.
Yeah.
3 significant figures stored.
20.1 seconds. Okay. Maybe I'll go dressed up as a calculator. I could, like, get some cardboard boxes, painted grey, write Casio 991 on the top. I don't know. Part of me wants to be a troublemaker, dress up as like something racist or something, but I don't think I can, Like the Canadian Prime Minister, you've heard about him? Yeah. And I could say, no, I'm just dressed up as a Canadian Prime Minister who's dressed up as someone racist. I'm not dressed up as someone racist. I'm just dressed up as the Canadian Prime Minister, But I don't think I should do that in an international school, so I'll have to think of something else. It'd be risky. I could try it, but it'd be a bit risky, I think. No. So I need to think more.
Don't let it bite you later on in your life when you become Prime
Well, I become Prime Minister, yeah. And then there'll be pictures on Facebook. Yeah, no, I didn't. I've no ambitions to become Prime Minister, so I might be okay. All right, is this okay? We see how we got that? Yeah, Regina, this is okay? Are you sure? Yep, okay. So, that was really it. The two most important things is the formula and its proof and the experiment. So we've looked at how to use the pendulum to calculate the G. Okay.
The essay is not the lab report.
Hmm?
The essay.
The essay is not the lab report. The essay is just that, an essay on a physics topic. Actually, I need to check what physics topic I picked for you. It's going to be something like, maybe, I'll check on the computer. I think I picked an essay on the physics of snooker.
Oh, that should be
Maybe. I have to double check. I can't remember what it is. Snooker or baseball or some collision type of or bowling or something. It was, I remember it being about collisions, because I thought it'd be a chance for you to use all your vocabulary, like conservation momentum, collisions, elastic, inelastic, kinetic energy. You know, you could work in all your vocabulary into it. Okay, so like I said, we have just 1 hour tomorrow for physics, isn't it? On a Thursday, and we have 1 hour, less than 1 hour left today. So the best thing you can do to prepare for the mid-semester exam is make sure all those workbook questions are done. And I'm going to give you time to finish them now. And if you get stuck, we can do it on the board. Okay?
So everything is up to the pendulum.
Everything up to the pendulum. Yeah, I'm not going to start the next chapter until after the break, which is going to be materials. Density, mass, pressure, temperature, all this type of stuff. It's kind of it's pointless to start a new chapter 1 hour before the break, so we'll start it after.